we were going to look at an example of the use of Fano's inequality in the context of showing a lower bound for a certain kind of structure. This is not technically a data structure lower bound, but it's going to be a lower bound on space, which is a related thing that will make use of this sort of this first formless argument that, namely, if you can make this large enough, then this has to be large enough, and therefore a certain size has to be. And so the problem, the test problem we're going to be using was this problem of dimensional reduction in L1. Like I said, the question was, if I give you a set of n points in L1, and I want to embed them into a low dimensional L1 space, how low can this dimension be? And the motivation was that, for various reasons, dimensional reduction is a nice problem. And for L2, we know how to do this pretty well. That you can get something like log n over epsilon squared if epsilon is the error, the relative error in your scaling of the distances. Because obviously you're going to face some error. You can't do this isometrically. And so the short answer to this problem is you can't do this. And that D is basically going to look like, and this has been known even before this paper, that D is going to look like some polynomial in n. Okay? Some function of epsilon here. The actual form doesn't matter, but it's going to be very large. And at any rate, it's not going to be logarithmic. It's going to be exponentially worse. Right? So this has always been the annoying thing about L1, that doesn't have those nice properties that L2 has. That, you can think of this as the source of all our pain in computer science, is that L1 does not embed nicely. Anyway, so how can we use? So how is this argument shown using Fano's inequality? Okay. So the typical argument, right, for these things is that in most of these proofs, and this is no exception, is to say, okay, let's build some kind of graph, because you can think of graphs as embedded on some parts of the Hamming cube, and Hamming cube is L1, so it's very easy to show for these graphs that they can be embedded into L1 isometrically. So they are the distant. So in other words, construct some graph. So step one usually is construct some graph, and with appropriate weights, such that the shortest path metric on the graph, so where the distance between 2 points, the shortest path distance between them in the graph, is in L1 isometrically. Okay, and again, this is a fairly intricate construction that I will not be getting into. This is something that the actual paper details, but it's not as important for how we want to say it here. For those of you who are familiar, this is sort of generalization of the so-called diamond graph and things like that. So you show this graph, and then you show that somehow this graph cannot be embedded. Cannot be embedded with small distortion into L1D for small d. Okay? And so we're going to focus, what I want to focus on, of course, is the second part. It'll turn out I can actually get pretty far into the argument without even knowing what the graph looks like, because what he quickly does in this proof is convert the graph into something more abstract. Okay?
So one historical footnote is that what is mentioned that the way he got this result was that he was in Paris attending a talk.
Here?
Here. And then he realized that maybe I could use Fano's information theoretic arguments and get a baby who was walking around in the city, and he conceived of the proof while walking around here. Excellent.
That is the best story ever. So yes, so don't attend this talk, go out and walk, and you might come up with some more results. So there you go. So this proof has a nice local context to it. So let me see what I'm happy with erasing. So let me keep that so I can erase this stuff here. So. Okay. So again, like I said, the first step is to take this graph and play some games with it. It's like a fairly involved graph that can be encoded using 0-1 bit sequences, so you can get the Hamming property that you need. But let's assume that that the original graph. So all we need now is to assume that the original graph, the edges of the graph in particular, edges of the graph are represented as elements of the set 1 to 2k to the n. This is a bit confusing. I'm going to change this n to capital N, okay, so that I can use small n here. Okay, so capital N in this setting will be basically 2k to the n. Okay, so think of so in particular, each edge of the graph is going to be represented by some element of of this space, okay? And so the mapping into lower dimensions, so whatever mapping I have is going to be a mapping of this into something in d dimensions. Okay, essentially the edge is going to be a subtraction of two things. So what we're looking for is a mapping that goes from 2k to the n to d, okay, for some d. Sorry, 1 second. Yeah, not a d-dimensional, sorry. To some d-dimensional vector. This is going to be, well, this is actually going to be a bit more, yeah. No, so what happens is that he maps the vertices, and the edges end up being the subtraction of the two encodings for the vertices. So it's a bit easier just to think about it this way. But that's really what's going on, yeah. Because it just makes the analysis a little bit easier. So this is what some kind of mapping we want, right? You want a mapping from some object here to some object here in this d-dimensional space. And in fact, just to make the proof a little bit easier, or at least that's the way he starts off. He says, okay, let's assume for now that not only is it in RD, it's on the simplex. So in other words, a set of all points whose coordinates up to 1, okay? Which is convenient because then you can think of this mapping as a mapping from this point into a distribution over 1 to d. Right? So you can think of this as some point in this as being some p1 to pd. So you can think of this as a distribution over 1 through d. Okay? So, and he later fixes this assumption, so you don't have to have that assumption there. But for now, we work with that. Okay? So now, here is the process that he's going to start off with. So the whole x and y and encoding process he's going to start off with is going to be something like this. So the idea is think of an x that is sampled uniformly from that space here. Okay? So think of x as a sample from this space. So x is drawn uniformly from this space here. Okay? And f of x, so let me use small letters. So f of x is going to be some point in this, which we'll think of as a distribution over 1 through d. Okay? So think of y as sampled from f of x. Okay? So y is a draw from the distribution over 1 through d sampled here. Okay? All right. So if I want to apply right, so if I want to show a lower bound on the size of this data, or whatever representation I'm going to use, I need to give some kind of lower bound by a Fano's inequality on this object here. Okay. So I want to put some lower bound on this, and that will give me the lower bound that I need on the size of the structure, on size of D. And you can rewrite this expression because x is sampled uniformly from here. You can think of this as having n coordinates to it. So you can rewrite this as this is equal to I of x1 plus I of x2, y given x1, and so on. Okay? Just by the chain rule. And so if you can lower bound, suppose you can say that, okay, for some L, I of xl and y given x1 through xl minus 1 is greater than or equal to alpha for any L, then you can conclude that this quantity will be greater than or equal to n times alpha. This is what I was telling you, using the chain rule here. So the goal, therefore, is to somehow show this property here. Right? If I can show that for one of these things, that basically getting the next bit, essentially, the next bit of x from this information has a certain lower bound in it, I get the bound I need. That's the for all L. Yeah, so for any L. In other words, take an arbitrary L and do this. If I can choose for an arbitrary L, then this will, yeah. Yes.
So first, I mean, here you're not assuming any specific f in the problem.
Correct.
And second, I mean, why is this almost isometric?
It's not yet. It's not yet. No, no, no. I have not said anything about the isometric aspects of this. That's the part that I'm going to be hiding. But I'll tell you where I'm hiding it. I haven't hid it yet. Yeah. Okay. But you're right. Yeah. Okay. Yeah. There's no assumption F here, which is nice because some of the early proofs of this dimensionality reduction lower bound were only for linear embeddings. They had specific construction in them. This doesn't have that limitation on it. So. Okay. I'm going to leave this here. I'm going to rub out the other stuff here. Okay. So our goal now is to show that this mutual information is reasonably large, whatever that means. Okay. Note also that h of y is more than ixy, right? Because h of y is ixy plus h of y given x. And h of y is because remember, you can think of y as a draw from a distribution over 1 through d. Okay? So what's going to happen is that if I'm able to put all this together, I will get d is greater than or equal to something. And that's the goal I want. So if I can glue this and say this, then I get, one second, then d will be greater than or equal to 2 to the n alpha, and I'll get the lower bound I want on d. Yes?
How do you get h of y is less than?
Well, because, so y is drawn from a distribution over 1 through d. Remember, what I'm doing is I'm taking f, I'm mapping an element to an element of the simplex on d dimensions, right?
So that's a continuous space.
Yeah, yeah, but now I think of y as a sample from that distribution. Right? My y itself is not this. My y is a sample from this distribution. So y is drawn from 1 through d. No. So, okay. So let me draw some here. Okay. So I have my space here. My f maps into some space here. Right? And oh, I see. You're worried about the continuous entropy versus the discrete entropy. Is that what you're asking about?
I don't understand what is the exact relationship between x and y.
Okay, so I take x, and f maps it to the simplex. Okay, so this is some point of simplex. That point of simplex, because of the simplex, is also a distribution over 1 through d. Because now it's saying pi is the probability, you can think of pi as the probability of seeing I. So imagine if this was a 3-dimensional simplex, maybe I map x to the point 1/3, 1/6, half. Which is basically saying, okay, the probability of seeing, I can interpret this as the probability of seeing 1 is 1/3, the probability of seeing 2 is 1/6, the probability of seeing 3 is 1/2. Now I sample, and I get 3. That's my y.
What's the distribution for x?
Sorry? It's uniform over this. So x is assumed to be uniform over this space. Okay?
It's assumed the mapping is deterministic?
Sorry?
No, it's assumed that this mapping is deterministic?
F is deterministic. Yes. Yeah. Okay? So y is just the sample 3 in this case. Right? And so the entropy of y is basically the maximum entropy you can have over 1 through d, which is log d.
So when you say h of y, I mean, there are two interpretations. You are calling y as a random object, or you are calling y as the name of the distribution. Okay? And
Good. So I should have been more careful in my notation. This y was the actual sample. Y is a random variable whose entropy I'm talking about.
Y was never the distribution, right?
Right. F of x is the distribution, and y is drawn from that. Yeah. So this is okay. Yeah. Good. I mean, because this is kind of confusing, right? So I'm not f of x is not my object. Y is not f of x. Y is drawn from the distribution that's represented by f of x. That's the weirdness in this whole thing. That was not maybe clear, but I'm glad you asked that. So then there was a question back there. Is that clarified now? Okay. No. Okay. Good. All right. So again, if I can get this to be shown for any L, right, that this is true, then by plugging all this in, I'll get the lower bound on D that I want. Right? So all I need to do, is to show this bound here. Okay. All right. Right. So this goes back to the issue of, is F a reasonable mapping itself? I will get to that in a second. So the actual theorem says that F has to have a certain property that implies that it's a good high quality embedding. This is a very technical property on the graph that I've been pointing to stick, but you're completely right that there is this magic property that F has that ensures that it gives you a good distortion embedding, right? So it's not linear, but it does have some other properties on it. And one of the clever things in his proof is that he can actually write down this condition given his graph in a way that kind of makes sense, right? But it involves basically looking at pairs of vertices in this diamond graph, and it's kind of messy. Maybe your example that you were mentioning would be cleaner in the augmented index example, but.
I can say what the problem is that I think for which it's easier to augment it.
Sure.
I can chime in whenever.
Okay, when I finish this, maybe you can chime in. Yeah, that's good. So, okay. All right. So what we're left with here is, is this argument here. So we basically want to show that this mutual information is large. Okay. But now here's where we apply Fano's inequality. Because what we're saying is that if we want to show this is large, we'd like to show that this is small. In other words, that we have a good reconstruction procedure to reconstruct this next bit, XL, given all the information we currently have.
XL is a number between 1 and 2k, it's not a bit.
Sorry, XL is a number between 1 and k, not a bit. Yeah, that's right. Yes. Okay. And so this is where things get a little bit disappointing, because the rest of this argument, so the rest of the proof is basically a very detailed construction using the graph and using the properties of F to show that here's a reconstruction procedure that reconstructs XL with a certain probability. And so he puts a probability in here, applies Fano's inequality, gets his bound here, plugs this in here, plugs this in here, he gets the bound there. Okay. So again, it would have probably been more pleasant if I had gone through the details, but those details have almost nothing to do with Fano's inequality. They're again much more structural properties of the graph that we're dealing with. So I don't know if there's a way to put stuff online, but I can point the references to the paper and you can take a look at that if you want. The upshot is that, again, the whole argument boils down to using this inequality to give this bound and to get that and to get that thing here. Okay? Okay, here's what's coming in. So he gets to this point where he wants to show this lower bound. He invokes Fano's inequality to say, if I can show this number, which I'll explain in a second, to be small, then by Fano's inequality, this number must be large, and therefore all this will work. Well, what is this number? This is the probability of making a mistake when you reconstruct something from something. What am I reconstructing? I'm trying to reconstruct the nth coordinate of x from y and everything I've got so far. And so he gives you this reconstruction procedure and says it works with probability something, and then that whole thing just plugs in right there. Does that make sense? Yeah. Okay. All right. Good. So, like I said, next week Casper is going to talk about this concept of cell sampling, which is, I like to think of it as sampling plus Fano in some sense. And so one place where this is being applied now is in data structure problems. Again, I don't want to really steal his thunder, so I'll just very quickly sort of say something about that. The idea is that you have some kind of data structure again, and you're making queries in the data structure to answer a problem, right? So you have some space, the data structure has space S, and you make T queries into it. And what you typically want to do in these problems is say that, is there a lower bound on S times T, or some lower bound on S and T? Right, so how much, given a certain amount of space, how much query do I need? Obviously, if you blow up your space, then one query will give you all the answers. You just write them all down. Or if you don't do anything, then you do a lot of work at query time and you get them. So there's a trade-off between them. And so you want to prove lower bounds on this trade-off. And so the way Fano's inequality then shows up in this approach is that you basically say, I'm going to try and show, using properties of my data structure, that a small number of cells, often extracted through sampling, can answer correctly a large number of queries. Right, so suppose I do some sampling, I get a small number of cells, and because of some magic in my problem, they can resolve a large number of queries, which means that for a large number of queries, the cells that they hit at the data structure are only the cells that I picked. Okay, suppose that happens. That means that for those queries, I can reconstruct my answer very quickly, but these are a small number of cells, and this small number of cells that reconstructs answers very quickly must have high mutual information, so it must be big, and so the whole structure must be big. And then the clever part is playing games with the parameters to make sure you get a nice bound. So again, he'll say more about this next week. He'll probably have his own sort of interpretation of what's going on here. But one of the reasons why this is attractive that he mentions is that you can get lower bounds for data structures using communication complexity, right? And many of the folks in the audience have done this kind of thing. But it seems that for some problems you can get stronger bounds using this technique. Again, I'm not quite sure why. I've talked to some people about this, and it's not quite clear where the strength comes from, but it works in this case. Maybe there are folks who know about this in the audience. Okay, so that's all I want to say about data structure lower bounds. So this is, again, one example. There are other examples, and like I said, they're not always as clear. Well, maybe some not clear, and maybe now is a good time for you to explain this other example that you have. You want to use chalk? Yeah. See, this is the crowdsourced lecturing, so I get a drink now. So.
So this I think of as a simple example of the use of Fano's inequality in communication complexity. So Alice, this is again a one-way model where Alice has X and Bob has an index I, as well as the prefix x1 through xi minus 1. And the idea is that what we want to do is to be able to decode xi after Alice sends a single message a of x. Right? And you don't have to output xi, you want to just output it with some high enough confidence. So the reason sort of, this is so natural for, Fano's inequality and the chain rule is that you basically end up looking at the mutual information between x and a of x. And you want to say that this also would require omega n bits, so that you can't really say, despite knowing the prefix, it doesn't quite help. Right? It seems like, okay, how should this help, say anything about xi, right? But you have to be careful about what the side information is. Suppose I give you everything but xi, right? Then you can actually solve the problem. So if I also have the prefix and the suffix, I just need to send the parity of all the bits. That's just one bit of information, and then from that you can sort of recover this thing. So it matters that it's the right amount of side information that is still unhelpful. So anyway, just to let me quickly finish this, is that you basically would use the chain rule for mutual information, right? And this is sort of tailor-made for Fano's inequality with the right amount of conditioning that's happening. So you can see what's going to happen is that when Bob gets index I, he is able to recover xi given x1 through xi minus 1 and the message. And it's sort of, just plugging in Fano's inequality directly tells you that this quantity must be large.
So basically you give a small error for this, and then therefore this number has to be big. Yeah.
So it becomes n times.
Yeah. Okay.
Yeah. And there's some details, but that's essentially.
Okay. Cool. Thanks. Yeah. All right. If you wish, the dual version of thinking about this. So one way to think about this was, we want to make this big, so we'll make this small. The other approach, which is much more popular in Minimax estimation, is to say, I want to make this big, so I'll make this small. And then all the work goes into how to make this small in order to make this big. So let me explain how that happens, where it comes from. So this goes back to sort of basics of parameter estimation. Okay. So let's think of a classical sort of parameter estimation problem. I have some distribution P, and I draw samples x1 through xn from P. Okay. And there's some parameter of the distribution P, and I want to estimate it. So there's some parameter associated with P, right? This belongs to some parameter space, right? Let me use the different here. And I want to estimate theta from the samples I've drawn. So for example, I might want to estimate the mean of the distribution or something else. Okay. So of course, you not just want to know what the parameters, you'd have some notion of closeness, right? So let's say I define some metric. So there's some metric that I define, or semi-metric that I define on theta, right? And so I can define closeness in that sense, right? So let's say, and I have, so for example, I might say that if I have my true parameter, theta p, and I have my estimate theta hat, then I compute the distance between these two things. And I might scale it by some other function. So for example, this might be the L2 distance, this might be the square function, and so I just want to find the squared L2 distance. Right? So this is some kind of measure of loss, of error in my, or risk in my estimation of the parameter.
Why are there two such functions?
Well, rho is a distance, is a metric, and phi is some kind of scale function, right? So I mean, if I want to do the square of something, I can't get a metric to do that, so just, so just a convenience. Yeah. And so what you're doing this, you want to find the average error of this estimator. So you're looking at something like, you want to estimate this quantity. So the expected value over p of the distance between the true distribution, to true parameter, and the parameter you get from your samples. Okay, so this is the average error of your estimator over the samples, and obviously you want this to be good for all distributions, right? So you're going to look at this here. So I should say this is not expected, x1 through xn drawn over p, right? So this is the cost of your estimator. So if I have some magic estimator theta hat, this is my penalty I'm paying for it, and I want the best such estimator possible, so I want the inf of this thing, right? So I want an estimate that's good.
It's a universal estimator because it's not distribution free or whatever you want to call it.
I don't know what it's called, but
Because you were saying I should develop something that works for all p.
yeah, for all p, yes, yeah. I want some estimator that works for all p, yeah. So I guess, I don't know, is that what it's called, universal estimator?
Maybe it's distribution free. I mean, it's like you don't have access to p. That's what you were saying.
Well, I just draw samples from it. That's all yeah. I mean,
You don't know this.
you don't know it. Yeah. I mean, so in practice, p might be from some well-known class or something, right? But I'm not saying it has to be over all. Whatever your class of distributions is, you want to do it over that. So, and so you want you want to make this quantity as small as possible. You want to find an estimate that minimizes this quantity, right? So you want to have some lower bounds on this, right? So in other words, you want to have, you want to get, and let me write this down. So this gigantic sup, the sup over all p of this expected value, you want to be able to provide some lower bounds on this. Because by doing so, we provide a lower bound on the quality of any estimate you're going to provide. Because again, we're in the lower bound game here. We're saying how bad can my estimators be, okay? And of course, if you want to find a lower bound on the sup, one thing you can do is, since the max is at least as large as the average, you can say, well, instead of looking at the sup over all distributions, I would say I want to in fact I want to fix some indexed family of distributions PV indexed by some parameter V. So there's some parameter V that indexes a class of distributions, a set of distributions in the set. And I want to minimize, and I put some distribution on P of V, so there's some distribution on V. And I want to instead minimize this average cost. So it's going to be something like pi of V, pi of V, the expectation where x1 through xn are drawn over PV of this whole expression here. Right? So in other words, instead of lower bounding the sup, I can lower bound this average, sort of Bayesian average, if you want to call it that. Okay. Then the game becomes, okay, how do I find a good collection of P and associated distributions on sampling those distributions to get this bound here. Okay, this is a classic sort of minimax estimation problem. So that's the minimax expression here. So there's an inf sup minimax. And you want to lower bound it by doing this kind of thing. So all the minimax techniques sort of boil down to this kind of thing.
Or you mean to say something that if I can estimate the parameter, then I can kind of I have some information about which PV I've chosen?
That's where the lower bound is going to come from, essentially. So what you're going to do is, you're going to reduce the estimation problem to which PV have I come from, which V have I got, exactly. So I'm going to show that next. Good. Yeah. This min. You want to find the, if you want to find the min over estimators. And the goal is to find the min over estimators. So for any particular estimator, this is your worst case bound. So it's again like a worst case, best case thing, but an average. Okay. And as he sort of correctly pointed out, the trick is going to be to convert this to a testing problem. Just in the same way as we saw before, we want to convert this to a testing problem and then create this, use Fano's inequality there as well. Right? So So imagine now that you have some process where the universe, where first V is sampled from pi, right? So some parameter V is, or not, some index is sampled from pi, and then you, once you got V, you have PV, and then you sample x1 through xn. x1 through xn are sampled from PV, right? So imagine this process is what's happening right here, okay? And your goal is to find V. So there's a bunch of distributions. You get a sample. It's like, okay, which of these distributions did this come from? Okay, that's the game you want to play here. So imagine these distributions form a kind of packing in the space of parameters. What I mean by that is that, remember the space of parameters has a metric on it, so it's a metric space. So imagine these distribution as they correspond to some point in that space. So if I draw the space here, and this is the metric space of parameters, imagine distributions kind of look like this. In other words, each of this is 1V, this is V1, V2, V3, and they're sufficiently far apart. Okay? In particular, let's say that any two distributions are at least 2 delta apart for some number delta. So in fact, imagine, in other words, construct a collection of distributions that have this kind of well-separatedness property in the parameter space. Question? I see a fierce frown. This space. The big circle is the metric space on the parameters. Okay? Right? Distribution, yeah. Or, distribution or theta of, so think of this as theta of P of V1. And this is the parameter for theta of P of V2. And this is the theta of P of V3. Right? Okay? And they're sufficiently far apart, right, in parameter space. So they're yeah. Okay? All right? In some sense, this is, you think this is a good thing. If, this is, okay, so there are two spaces here. There's the distance space of the parameters, and there's the distance space of the distributions themselves. And what this is going to do is play some games with these two spaces. Okay? The distance space, the distributions are separated in the space of parameters by this construction here. But what you want to do if you want to make them indistinguishable, right, is somehow make them close in a different distributional space. Okay? And that's what the intuition is. In particular, if you have a collection of distributions like this, you can actually bound this quantity here over this class of distributions in the following manner, that so for any, if you have such a family of distributions, then the inf sup of this average error, okay, is always greater than or equal to that function phi of delta times the probability, right, that, the inf, delta is your radius of these packing balls. Yeah. Inf over all, suppose so you have some reconstruction procedure that finds V from this sample. So let's say some procedure G. So this quantity is greater than or equal to this term times the probability that G of x1 up to xn is not equal to V. Okay. So again, it's not basically to prove this fact, given these distributions, you just need to use triangle inequality and the fact that, if you're in some range here, your estimation error is going to be bounded by this. Because think of it this way. If you're trying to estimate, if you make these balls big, then you could make a mistake in your estimation by this much. Your cost will be bad because you're far away, but your reconstructions will be good because the distributions are far from each other. So that's where this term comes from. So if delta is large, you pay more error in your estimation cost, but this is your reconstruction cost here. two terms. And what's interesting is the way these two things reflect the tensions in this. So as we alluded to earlier, right? These distributions are far apart in parameter space. What does it mean for them to be close in some distribution space? So let's say our distribution distance is the KL divergence, for example. Okay, so you measure the distance from A to B by the KL divergence from A to B. And if you want to make them all close, oh, sorry, the Kullback-Leibler divergence. So, I'll define it when I need to. Black box information theoretic distance between two distributions. Let's say where it's larger if they're further and it's smaller if they're closer. But I'll define a bit. It turns out that if you now say I have a collection of distributions, now I'm in a distribution space, not in the parameter space, and I want them to be close to each other to increase this quantity, it's known that, and this may be where I should define the Kullback-Leibler divergence. So the Kullback-Leibler divergence between distributions P and Q, and I want to define this in a discrete setting, is equal to sigma Pi log Pi over Qi. It's one of the sort of more, it's called the relative entropy or the cross entropy. It's sort of it's a standard distance between distributions. It's not a metric and it's not symmetric, but it's nice. Then, if I have a collection of distributions and I want them to all be kind of close to each other, one way to say this is that their one median should be small. That makes them all close. And if you take the one median of the Kullback-Leibler divergences, the thing that minimizes the sum of the Kullback-Leibler divergences, that number you get, the sum of the distances, is the mutual information of these distributions. Okay? So I went through this very quickly. So what I'm saying is the following. What I want is to increase, if I want to increase this error here, okay? What Fano's inequality is telling us, right, is that if I want to increase this, I should decrease this, okay? And so what I'm trying to do is give you geometrically, what does this mean? If you have a collection of distributions PV, so there's a collection of distributions P1, P2, all here, okay? And I want to increase the reconstruction error of finding which of them come from. So intuitively, we know what that means. They're going to converge together, right? They're going to be almost the same. If my two distributions looked almost the same, it's going to be very hard to tell apart from samples which of the two I'm in, okay? But if I want all of these to be close together, I know that I have to reduce the mutual information. But if you think of the mutual information as the average KL distance from these points to some center, to the average of all the distributions, that's effectively what's going on. So you're reducing mutual information by pushing all the distributions together. So you push the distributions together in the distribution space while keeping the parameters apart in the parameter space. And that's how you construct a lower bound for this problem. And that's reflected in these two terms here. And that's how minimax estimation gets done. The clever part of it is coming up with such a family to make this happen. Okay. I think it's a good point to sort of stop and sort of take some clarifications, questions before I go any further. I want to do an example of how this is used, not in statistics, of which there are a gazillion examples, but again in computer science, because that's what I know, and I think it's kind of nice to see it show up there. But before I do that, I want to stop here and sort of take some, yeah.
So KL is not metric, so...
No, it's not.
But then how do you apply what you...
Because remember, this is the metric on the parameter space. You can think of this L2 if you want. The KL I'm reasoning about in the space of distributions. I'm not saying, it's not a metric. I'm not using any metric properties there. I'm merely saying that I want the distributions to be close, by which I want to say, and there's a reason I want to say it this way, because I'll be using it later, is that I want the average distance to the, I want to find a distribution that minimizes the average distance from all of these, and I want to look at that cost. So it's almost like saying I have these distance functions, and I choose some point in the middle, so that I minimize the sum of all these distances. That's why I call it the one median. You don't need to have a metric for that to define that quantity, because I can define the distances as directed distances into the median. And for KL divergence, that quantity you get is in fact the mutual information, which is a nice property of mutual information. It's sort of a nice geometric sort of way to think about mutual information as the average of these KL divergences.
Just to complete that argument, so once you achieve that way of clever construction, then you know that the mutual information is small, therefore
it becomes large,
PE is that one.
and then this becomes big, and then you win. You give a good lower bound. Yeah. So this is the opposite way of doing it, right? Before we were making this small to make this big. Now we're making this small to make this big. That's fundamentally how the statistics folks use it that way. In computer science, we use it the other way. Well, so far, but now it's all going to merge. Do I have 5 minutes or less? 5 minutes. 7 minutes. More questions before I go on to the example. I mean, depending on time, I may or may not continue the example right now. So, but I'm happy to sort of take general. So again, to recap, right? The goal of Minimax lower bound, to do Minimax lower bound analysis, is to give lower bounds on the risk of an estimation procedure to estimate a parameter. In order to do that, you want to lower bound this quantity here, which is the worst case error you're getting for any distribution in a class for your fixed estimator. In order to do that, we're going to replace that by just an average over a fixed indexed set of distributions to make it easier to think about. And then we're going to say that indexed collection of distributions has to be constructed in a nice way, because if you have this, if they're sufficiently far apart in the parameter space, you pay error in terms of that. And if they're sufficiently close in distribution space measured by mutual information, you pay error in terms of that via Fano's inequality. And that's how these bounds get used. I should say, though, that Fano's inequality is only one of many such mechanisms that are used to show minimax lower bounds. And I will talk about that in a bit. But this is the one way of doing it. Yes?
Maybe just about familiar with the scale versions. You have P and Q are vectors of...
Yeah. Think of them as discrete distributions for now. You can...
And we know that... Why do we know the point?
Why do we know, sorry?
So you're looking at the probability of getting some value I in some range, and then you're saying P is this distribution, Q is this other distribution.
Right.
Okay.
Right. Yeah. And again, all these can be defined in a more continuous setting, but that's my feeling as well. My brain doesn't work that way, so yeah. Sorry?
That's not our problem.
Well, there's probably some people in the audience room, it is their problem, but it's not my problem. So yeah, that's fine. Okay. Yeah. Okay. All right. So we have a choice. I think we have 5 minutes, and I could define the problem that I want to look at, or we could, I don't know, can you have the option of breaking early and starting early, or breaking early? How do you want to do this?